Michio Kaku says a question that preoccupies us so much is this: can the flow of time split? Can it form different branches, loops, and wind around itself? If so, time travel is something we must take very seriously because Einstein's equations allow travel through time. And today, we're going to show you that time is so much more than the hands on your watch. After all, it could be that something like time doesn't even exist. And before we get misunderstood, this assumption isn't the core of some crazy fringe theory. It's a concrete result of a new research study. But how is that even possible? Why could what we generally understand as time actually be just an illusion of quantum physics? And what conclusions can be drawn from this incredible thesis? Be sure to stick around until the end and find out with us. Let's start with a small but profound quiz question. What is time anyway? Although time seems so mundane in our everyday lives, very few of us have ever given this complex topic much thought. Albert Einstein certainly had his own unique perspective on the matter. He said, "For us physicists, the distinction between past, present, and future is nothing more than an illusion, albeit a persistent one. Subjective time with its insistence on the present has no objective meaning." But conveniently, this persistent illusion can be dressed up in a corresponding definition. Namely, time embodies a physical quantity that describes a sequence of events in a clear, irreversible direction. And that doesn't just apply to the numbers on our clock or the pages of our calendar. It applies to literally everything. After all, the cosmos itself moves not only spatially but also temporally. More precisely, from its beginning, the Big Bang, to its end, time therefore proceeds in a strictly linear fashion. An American physicist, John Wheeler, once summed it up by saying that time is what prevents everything from happening at once. We experience the passage of time as irreversible in one direction. The future can be changed, the past cannot, and the two are separated by the present. So far, so clear. But if we take a closer look at this fundamental quantity, we quickly see that time is not quite as simple as it seems. From a purely physical point of view, it probably embodies one of the most difficult units to define. As Einstein explained over 100 years ago in his special theory of relativity, time is relative. In other words, it can be stretched by strong acceleration forces or gravity. As a result, we can only compare periods of time under similar conditions. And indeed, a measurement taken a few years ago showed that time itself passes a tiny bit faster on mountain peaks than in the valley due to Earth's gravity. As a brief interim conclusion, it can therefore be said that time is, to put it cautiously, complex. And to understand why it is still at the center of scientific debate, we should take a look at how experts approach this topic. As mentioned above, there is of course Einsteinian physics, which explains the processes of the universe on a large scale. Quantum mechanics, on the other hand, deals with events on a small scale, and the two approaches often seem to contradict each other. Let's take a look at Schrödinger's cat, one of the most famous thought experiments of all time. In this experiment, a cat is locked in a box with a lethal poison capsule, but no one knows when the poison will be released. Against this backdrop, the cat can be considered both dead and alive at the same time because its state would only jump to one of the two states through direct observation. In detail, the physicist Erwin Schrödinger, after whom the experiment is named, wanted to demonstrate the incompatibility of quantum mechanical and classical physical principles. In fact, quantum mechanics also recognizes the superposition of different states, and the corresponding system only assumes one of the superimposed states when a measurement or observation is carried out. Applied to Schrödinger's cat, however, this is problematic, to say the least. After all, a cat cannot be dead and alive at the same time. The strange field of quantum entanglement, however, in addition to superposition, quantum entanglement is also part of the whole truth of quantum physics. But first things first, in general, particles in normal quantum theory do not have a definite state. One can only assign them relative probabilities of being in one state or another. After all, this only changes in the context of a measurement when the particle assumes one of these states according to its probability. And as if this idea were not strange enough, things become even more mysterious when we consider what happens when two particles interact with each other. In this case, they can become entangled. This means that their individual probabilities are no longer independent of each other, but are linked. Let's look at the following example to understand this better. In an experiment to demonstrate entanglement, two electrons are generated simultaneously in their spin, or in other words, their intrinsic angular momentum is measured in two different devices. Ultimately, it turns out that the electrons have opposite spins, which is all the more astonishing given that, according to superposition, their state was not yet determined at all until a measurement was made. Ultimately, it was a measurement that caused one particle to decide on one state and the other particle to decide on the other state at the same time. Despite their spatial distance from each other, the two electrons are therefore to be understood as a coherent system. The problem here, however, is that quantum entanglement also violates the assumption of locality. This states that processes only have an immediate effect on their direct spatial environment. But in the world of quantum entanglement, entangled particles can be light years apart and still be inseparably connected. But that's not all. The exchange of information between the spatially separated particles also takes place instantaneously, in other words, without any time delay. For this to work, however, the information must be transmitted at faster than light speed, which is probably why it is not particularly surprising that Einstein had his problems with this effect, which he himself described as spooky action at a distance. Does time not exist? To say that the principle of quantum entanglement seems challenging would be an understatement. Despite this, it has recently given researchers a unique opportunity to take a look at the true nature of time and perhaps even to show that something like time does not actually exist. But first things first, as mentioned above, according to Einstein, time can be distorted and stretched by gravity and speed. In quantum mechanical systems, however, it appears to be unchangeable and external. It therefore embodies a fixed phenomenon, an unstoppable flow from the past to the present. However, time itself remains outside the wondrous and constantly changing quantum systems, and can only be recognized by observing changes in external entities such as the hands of clock. We are therefore dealing with fundamental contradictions that make it extremely difficult to reconcile the two physical theories. However, since extremely complicated does not necessarily mean impossible, researchers at the Italian National Research Council have been researching ways to solve the problem of the missing connection. In doing so, the experts drew on a mechanism that was proposed more than 40 years ago by physicists William Wootes and Don Page. The Page-Wootes mechanism postulates that time itself arises from a relationship between one object and another that serves as a clock. In other words, the two physicists suggested that time should not be understood as an absolute external quantity, but rather as something that arises from internal correlations within a quantum mechanical system. The basic idea is to mentally divide a large closed quantum system, such as a universe, into two subsystems, a small subsystem that functions as a clock and the rest of the system that one wishes to observe. And although the overall system remains unchanged in and of itself, correlations between the state of the clock and the state of the rest of the system can occur within it. This is because when the state of the system is viewed conditionally on a certain state of the clock, it appears as if the system is developing normally in time. However, this time is not an external parameter but arises solely from the entanglement and correlation between the clock and the system. The movement of change is therefore perceived relative to the clock, or in other words, from the perspective of an internal observer. Time appears real even though it does not exist in a larger context. For a non-entangled system, however, there is no time at all, and the system perceives the universe as frozen and unchanging. With this information in mind, we can return to the scientist's experiment. By applying this mechanism to two theoretical quantum states, a vibrating harmonic oscillator and a group of small magnets serving as a clock, they observe that their system can be described by the Schrödinger equation without explicit use of time. The researchers then repeated their calculations twice more, assuming that first a magnetic clock and then the oscillator represented macroscopic, or in other words, larger objects. Their equations simplified to those of classical physics, suggesting that the flow of time is a consequence of entanglement even for objects on large scales. Against this background, the experts emphasize that the correct and above all logical approach for them is to start from quantum physics and understand how to arrive at classical physics from there, and not the other way around. However, other experts have expressed skepticism. Although it's mathematically consistent to imagine universal time as entanglement between quantum fields and quantum states of 3D space, no one knows whether this picture will yield anything new or fruitful, such as modifications of quantum physics and general relativity. But we do know that your click will result in a new fruitful subscription. Simply click on the thumbs up and subscribe now to never miss a new video. We'll see you soon.